So, do you remember in calculus when somebody told you to integrate this? And then you try U substitution, you try a bunch of other things, and you find out that you can't integrate it. So it turns out that this is something in Calc 2, this is something that we couldn't integrate. But there are some applications where there are functions that look like this that we needed to integrate. And if we put limits, we can certainly use an approximation using, the left-hand rule, right-hand rule, and all that stuff. But in general, sometimes it might be important to just see what this function might look like. And so, although we don't have what's called a closed form function for this, we don't have it. We didn't have it, but then over time, somebody kind of defined it. They call it the error function. So although we don't have a nice closed form function for this, what people have done was if there's a function that doesn't have a closed form, sometimes you can express that as a series. And if you're able to express that as a series, you can use that series to at least approximate how this function is going to look like. Like if I wanted to graph the integral of this thing, I can graph it. I can graph it approximating using my power series. So that's the idea behind power series. And when we're solving differential equations, we've noticed that a lot of our differential equation processes require us to integrate things. And there's certainly things that we can integrate and we can find solutions for, but there are some things that are going to be difficult. And so this is kind of like the same idea. It would be good to have a power series approximation of it, at least to see how it might look like over a small enough interval that we're dealing with. So this, by the way, in Mathematica is defined to be the ERF function, error function. And if you type that in Wolfram Alpha, this is what you'll get. Oh, the square root business. This is another cool trick that you can try to use some tools from Calc 3 to come up with that square root of pi business. Anyways, I feel like talking about all kinds of other stuff now. By the way, this integral or something similar to this integral comes up in statistics. It's the bell curve. You guys have heard of the bell curve. With some constants, appropriate constants, and I think it needs to be a negative x squared up on top, then it'll end up being the actual bell-shaped curve known as a normal distribution. All right, so that's our little motivation, and we're going to have more motivation later on in why this is important. And so what we need to do is we need to talk about power series, and we should know a handful of power series off the top of your heads. If you don't remember them from Calc 2, we'll see if we can try to remember them. But to me, power series kind of stems from Taylor polynomials. Have you heard of Taylor polynomials? So Taylor polynomials are a way to express a function as a polynomial up to a certain degree. And what you're doing is you're kind of approximating that. So we have an e to the x here. Let's get started with e to the x as a Taylor. Well, let me tell you what the formula is for the function. So if you have a function f of x and a center point, doesn't have to be 0. Usually it's easier if it's around 0. Let's just call it a center point. X is equal to a in the domain of this thing. Then f can be approximated near a is approximately equal to f of a plus f prime of a x minus a. Now if I stop here, I'm not done yet, but if I stop here, I don't know if this looks familiar to anybody. Does it look familiar to anybody? Linear approximation. It's what? It's linear approximation. So it's like a linear approximation. In fact, it is a line. This is your tangent line if we stop here. And what you're doing here is you're looking at the slope, and then you have x minus a, and then you have y minus y1 if you bring the f of a over to the other side, and then that's really just the equation of the tangent line. But we're going beyond the tangent line, so we're going to a higher degree. So this eventually follows a pattern, f prime of a divided by 2, and later on we'll call it 2 factorial. But in this case, we can think about it as 2 or 2 factorial x minus a squared. Now, if we stop here, which again we're not going to because we're not done yet, if we stop here, what we have here is this is double prime. What we have here is a parabola, and graphically we can think about this as a tangent parabola. It's a parabola that best takes the shape of that graph around a particular point. And so, again, we're not done yet, so we'll add another term to it. And this time it's going to be the third derivative, evaluated at a, and then this time it's divided by 6, which happens to be 3 times 2 times 1, times x minus a to the third power. So again, if I stop here, we have a cubic function, and this is the tangent cubic function. It's a cubic function that's tangent to the curve at the point A that best describes the graph near the point A. And so we see a pattern here, and if this is a finite polynomial, then we stop at a particular value n, and so we can say f. And remember that if you have a power that's in parentheses, that's denoted as the derivative, the number of derivatives, evaluated at a again, divided by n factorial x minus a to the nth power. So this function can be approximated by this nth degree polynomial, and this would be a tangent polynomial, whatever that polynomial looks like. Okay? Have you seen pictures of this? Did you have a cool Calc 2 teacher that showed you pictures of these things? Oh wait, that was just me. I didn't have any of you guys for Calc 2. Anyways, so this is a good approximation for x values near a, which means everything revolves around this a business. I should have had a graph of this ready in Mathematica, but I don't know how long it'll take me to program that real quick. So this is a Taylor polynomial. So with a Taylor polynomial like this, we can find polynomials for certain functions. Or before we do that, let's if we let n get larger and larger, then we have what's called a Taylor series. So now we can think of this polynomial as going on forever. We can think about this as an infinite polynomial, which goes on forever. And we got a Taylor series. And if we have a Taylor series, that approximate sign is going to become an equal sign. And then instead of writing an infinite number of this thing, I think when we're talking about series, and this is going to haunt some people, I'm sure, from Calculus 2, we start by using the sigma notation to express the fact that we're going to be summing an infinite number of terms. And I'll use k for my index, going from 0 to infinity. Now, if I follow my pattern here, this is the kth derivative at a value divided by k factorial times x to the a, x minus a to the kth power. Now, a couple of things kind of make this work. When we talk about the zeroth derivative, what is the zeroth derivative? It's just the original function. You're not taking the derivative or anything like that. And then another piece of information, fact, that we should all know is that 5 factorial is 5 times 4 times 3 times 2 times 1. That's how it's defined. 1 factorial is 1, but what's 0 factorial? 0 factorial is equal to 1. Okay, so let's just don't have time to prove that right now, so let's just call that a fact. In fact, if we were going to try to prove this, it involves a gamma function. And again, we don't have time. So this is a series, a Taylor series. Now, with this, you can expand a handful of important functions. Now, expanding polynomials isn't really that big of a deal because polynomials are polynomials at n, and these are polynomials. So we don't usually expand polynomials. But if we take a look at non-polynomial functions, like the exponential function and sine, cosine, and any other combination of those trig functions and logarithms and things like that, then we can see the expansion. We can try to imagine what the expansion might look like. By the way, if a is equal to 0, we call this a Maclaurin series. Oh, there's one more, by the way. By the way, this equal sign holds for some sort of interval around a. And this idea that it satisfies a small interval around a, we get to define what's called a radius of convergence. That sound familiar? Yeah. So radius of convergence, we figure out radius of convergence, and then we figure out the interval of convergence and things like that. I don't think we're going to be too concerned about the interval of convergence, but we are concerned about the radius of convergence because we want this to converge at some point in some area. So this equality is going to hold for some sort of interval where a is in the center of it, and then it goes outward. Okay. So I guess the next step is to take a look at a few examples, and just to make things easy for ourselves, we're going to be looking at Maclaurin series. So we're going to be taking things around 0. So let's take a handful of functions that we all know and love. We'll start with the exponential function. Now, we can find a pattern for this, or we can just try to see if we remember it. This is one of the easier ones. But let's do a little bit of side work over here to try to figure out if we can find a pattern. Just side work over here. And the original function is e to the x, and f evaluated at 0 is 1. The derivative, conveniently enough, is e to the x. So the derivative evaluated at 0 is still equal to 1. In fact, all the future derivatives are going to be e to the x, so all those derivatives evaluated at 0 is still going to be 1. So in terms of following our function here, this is going to be 1, 1, 1, 1, 1, etc. So once you know this bit of information, then we can easily construct this Taylor series for this, or power series. So we have 1 plus 1 times x minus 0, so I'll just call it x, plus 1 over 2 factorial times x minus 0 squared, plus 1 over 3 factorial times x to the third. And once you get to the third, maybe go 1 or 2 more times, you see the pattern, right? And so this is easy enough to simplify as 1 plus x squared over 2 factorial plus x to the third over 3 factorial. And we can go dot, dot, dot here. And if you get really good at this, you can try to figure out what the generic term is. So the kth term is going to be x to the k over k factorial. By knowing this x to the k over k factorial, this is going to allow you to write this as a power series with the summation sign, k going from 0 to infinity of x to the k over k factorial. Now, to find a radius of convergence, and we'll do this little exercise to remind you how to find the radius of convergence. What we do is we use a tool or a test, or is it called a test? Yeah, it's called a test. A test called the ratio test. Remember the ratio test? So there's several tests. There's ratio and root test, which are used kind of interchangeably because they produce the same results. And there's a handful of other tests that, if you remember in Calc 2, that we won't have to worry about. Comparison test, the integral test, and all those other things. So we don't have to worry about those. That's good. And so we really just focus on the ratio test. So I really want you to know the ratio test because apparently it's in the homework. So the ratio test is you're going to take the limit as n or k. Let's use k. Goes to infinity of the kth term. Let's call it a sub k plus 1. The k plus first term divided by the a sub k. So you're taking a ratio of 2 consecutive terms, and then you're going to figure out what this is going to equal to. And the way you're going to do that is that if you imagine the k plus, this looks like it's the kth term right here, ak. So ak plus 1, you'll just change the k into k plus 1. So let's call it x to the k plus 1 power divided by k plus 1 factorial divided by x to the k over k factorial. So you have ak plus 1 and ak. Now, a lot of times, well, this is just some simple algebra where you multiply by the reciprocal. But by doing this, you can see things cancel. You have x to the k plus 1 over k plus 1 factorial times k factorial over x to the k. Now, if you remember doing a bunch of these problems in Calc 2, you'll see that the k, the x's, there's one extra x in the numerator than it is in the denominator, so you'll have an x out here. By the way, I'm sorry, these are all absolute values. And since k goes from 0 to infinity, then we don't need to worry about the absolute value around k. But what do I have here? I have k factorial over k plus 1 factorial. So it might be hard to picture, but remember that n fact or 5 factorial is 5 times 4 times 3 times 2 times 1. I can write them all out like that, but you can also think about k plus 1 factorial as k plus 1 times k times all those other numbers less than that. Yeah. So the bottom can be seen as k factorial times k plus 1. That will allow you to cancel all those other k's. And so you have the limit as k approaches infinity of 1 over k plus 1 times x. What? And as k goes off to infinity, there's a k in the denominator, there's no k on top, so this is just going to go to 0. Now, what do you remember from Calc 2 about the radius of convergence? If you take the ratio test, it's equal to 0, what happens? It converges for what? Yeah, all real numbers. So it turns out that if your ratio test gives you a 0, then it's going to converge for all real numbers. Okay? So we have an e to the x that has a particular power series. And if you don't have it memorized, memorize it now. And this thing is going to converge for all real numbers. Okay? So long as you go all the way to infinity. If you stop at any point, then this is just going to be an approximation. All right, we good? All right, let's do sines and cosines. And again, let's do this as a Maclaurin series, so around 0. Now, we need to know the derivatives of these things, right? So let me get this set up to see if we can. This is a lot of this stuff is all about developing a pattern, and that's what you have to do is you have to look for patterns. And this goes on to differential equations when you start using these things to solve for differential equations. So we have your original function sine x. The first derivative is cosine x. the second derivative is negative sine x. The third derivative is negative cosine x. And then if you take the fourth derivative, what do you get? You get sine x again, so you see that this thing loops after 4 turns. And then the fifth derivative is cosine x. The sixth derivative is negative sine x, etc. Yeah, so the purpose is to find, one of the ways is to find a pattern. Now, we're interested in evaluating this at 0, so let's evaluate this at 0. F of 0 is equal to, oh, it's sine x is, sine of 0 is 0, right? At 0, cosine is 1. Sine is 0 again. And negative 1. And then there's your pattern. It goes back to 0. Okay. So, let's see if we can write this out. Sine x is equal to, it's f of 0, which is 0. Let me put a 0 there just so we don't get too confused and keep track of the 0th derivative. And the first derivative is 1 times x minus 0. The second derivative is 0 over 2 factorial. At 0, it's going to go away, but let me just put all those other numbers there just so we don't get confused. And then we have a negative 1. Are we good here for a pattern? Do you think we can, should we go 3 or 4 more? Okay, we're good with a pattern. I'll put dot, dot, dot here, and let's see if we can simplify this a little bit. So we have x. Now, first of all, if it's an even derivative, we see that it's either going to be sine or negative sine, right? Which means evaluated at 0, it's going to go away. And if you're still not quite sure, this dot, dot, dot here, why don't you erase the dot, dot, dot and fill it in if you're still not quite sure about the pattern. Okay, so if it's an even derivative, then it's 0. If it's an odd derivative, then it's either 1 or negative 1. It just alternates. So the first one is a positive 1 times x. And then the next one is negative 1 times x cubed over 3 factorial. And so the next term is going to be a positive, what? X to the 5th over 5 factorial. It's still matching the power and the denominator matches. X to the 7th with a negative, and then 7 factorial. And then we can go on. Now, it would be helpful, I don't think it's that big of a deal, but it would be helpful if you can write this in the general term so that we can write it as a summation. And this can come in a couple of different flavors because it's only accounting for the odd numbers, but we can certainly get something down here. We could say k goes from 0 to infinity. Now, we have a negative 1 because it's alternating, so it's negative 1 to, now I want to put either k or k minus 1. So I want to make sure I match the sign with the first term when k is equal to 0. When k is equal to 0, that's the other thing that I'm not counting k. This is k equals 0, k equals 1, k equals 2, k equals 3. That's another difficult part about trying to write this nicely in a summation, because you're not, each k isn't the first derivative, second derivative, third derivative. It's not in that order anymore. So, okay, back to the question. When k is equal to 0, I want to have a positive sign. When k is equal to 1, I have a negative sign. So what do I have here, k or k minus 1? I think this is just k. And then I have x to some odd power, k, I think it's going to be what? 2k plus 1. So when k is equal to 0, I have 1. When k is equal to 1, I have 3, etc. And then it looks like the power in the denominator factorial is just going to match, so I got 2k plus 1. Okay? What? After today, because today you're looking at this and you're thinking, oh shit, that looks hard. But you're going to write it down, look at it tonight, watch the video, look at the notes, and say, oh, by Thursday you got it. Thursday's our next class time, where it becomes exponentially more difficult than this. This is all review. Yeah. And I know it's been a while, like last semester for some people, or 4 years ago, but we need this as a foundation to get through the rest of this chapter. And so, and this, you know, a lot of this won't really be covered, and you're just going to be asked to memorize a lot of these things or just know it. So by the end of today, we're going to write down a list of particular series that you should have off the top of your head, and so that when you see a series that looks like this, you can just say, oh, that's just a sine function. Something like that. Anyways, we have the sine function now. It looks like this. Think about the sine function as an odd function. The sine is an odd function because it's symmetric about the origin. And because it's an odd function, if you look at the powers of the x's, it's all odd. Okay? Funny how that works. So, are we good with the sine function? Let's do the cosine. What if I just say, you know, wave my hands and I just tell you what it is? With the same sort of, you know, same logic, same steps. Cosine is going to be equal to, oh, what is it? 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. And you can see that cosine is an even function and it has even powers and stuff. So k goes from 0 to infinity. It has an alternating sign again, so we have negative 1 to the k, or k minus 1, that's negative 1 to the k. We have x to the 2k, guarantees that your powers are going to be odd or even over the same thing, 2k factorial. Now, both of these, I didn't really talk much about the sine, but now that we're talking about this, both of these have a radius of convergence of infinity, which means this is going to work for all real numbers. The nice thing when you have a series that works for all real numbers is that you can take advantage of some series algebra. So let's actually there's one more series that I want to talk about, And that's the, what's it called? Geometric series. Are we good here for now? We got the exponential function, sine, cosine, or maybe I should talk about it now. Let's talk about it now. This is a little aside, and it's related to something that we've already done, so it's kind of exciting. So you guys got e to the x memorized already? This isn't hard to memorize, right? It's just 1 x squared over 2 factorial, x cubed over 3 factorial. It's all addition. Okay? Now, do you remember the imaginary number I? So the idea behind power series, or one of the ideas behind power series, is that if you know a power series, you can do a composition of power series. Like, actually, maybe I jumped too soon. I can find a power series for e to the x squared. Can I erase this one? We'll get to that fun part a little bit later on. This is more like business part right now. So e to the x squared is really just e to the x, and wherever you see an x, you're going to replace it with an x squared, right? That's all it is. So I have 1 plus, and then now wherever I see an x, I'm going to replace it with an x squared. So I'll put x squared there. And then I have x squared squared, x squared to the third power, x squared to the fourth power. I'll just stop here and go dot, dot, dot. So you can leave it like this, or you can make it look a little bit nicer, but bottom line is we have a power series for e to the x squared. So e to the x squared, e to the x to the fourth over 2 factorial, e to the, or x to the sixth over 3 factorial, x to the eighth over 4 factorial. And then if we find a general pattern, we can make it fit nicely into a summation sign. So k goes from 0 to infinity. The sign doesn't change, so I don't need to do a -1. I have x to the power is always even, and the factorial is half of the power. So this is your power series for e to the x squared. And then this would be a good place to tie in the very first thing I said when we started talking about power series, is that if I want the integral of e to the x squared, I don't have a closed form for that. But if I integrate this term by term, then I could express that integral as a power series. So let's do that. So if you're interested in integrating this, you would integrate your infinite series term by term, and integrating each of these, power functions is going to be a piece of cake, right? So the integral of 1 is x. The integral of x squared is, what is it? X cubed over 3. Integral of this is x to the 5th over 5 times 2 factorial, x to the 7th over 7 times 3 factorial, etc. I guess we should put a plus c there because it's an indefinite integral. It's a family of functions. So here's our power series expansion for a function that we didn't have a closed form to describe it with. Okay? So the idea with power series is that you can integrate and then differentiate it, and then we should get, you know, the corresponding derivatives and integrals. In fact, the fun thing to do, is to take the derivative of sine, the sine power series. Let's do that in our heads. Derivative of x is 1. The derivative of x cubed over 3 factorial, you derivative, right? So you take 1 off of the power, so it would be x squared. You bring the 3 down here, it'll cancel 1 of the 3, it becomes a 2 factorial. So you get x squared over 2. And then x to the 5th, take the derivative of that, it'll be 5x to the 4th, and the 5 and the 5 factorial will cancel, leave you a 4 factorial. So if you follow along that same kind of pattern, you'll see that the derivative of each of these terms will become each of these terms that will eventually represent the cosine. So derivative of sine is cosine. If you do it again, then it'll be the derivative of cosine, for example, will be the negative of the sine function. So it'll be the sine function with the signs reversed. Okay, so those are some of the handy things that you can do with the power series. Now, what I wanted to show you here is kind of just for fun. So just like we put x squared and replace everything with x squared, we can use our imaginary number like I and then times x and see what happens when you put I times x in here. Can you guys guess? Now, let's take a look. So the first one will be 1. Next one will be ix. Then it'll be ix squared over 2 factorial. So we'll need to figure out what that is. But we'll figure it out in a few minutes. So I'm looking at this top line here. And wherever I see an x, I'm going to put the ix. And to get the special effects for this, I think it's good to go maybe all the way up to 6 to see how this will turn out. Okay, so I'll just put dot, dot, dot after this. And let's do some little imaginary computations. What's I squared? -1. So I'm going to circle this and put -1 here. I'm going to replace that with -1. I cubed? -I. I to the 4th? Now, it's 1. I to the 5th? I times I times I times I times I. It's basically 1 times I, which is what? Which is just I. I to the 6th? It's a pattern. -1. So I'm going to replace those coefficients. Meanwhile, the powers just go x squared, x cubed, x to the 4th, x to the 5th, x to the 6th, right? So let's rewrite that. 1 plus ix. Now it's a minus. There's no more i's, so x squared over 2 factorial minus I x cubed over 3 factorial. And now it's a +1. There's no I again. X to the 4th over 4 factorial. And then this is plus I x to the 5th over 5 factorial. And then minus x to the 6th over 6 factorial. And if I underline the ones with an even power, And if I do something like circle, or I have underlined the ones that don't have i's, and I circle the ones that do have i's, I can split that up into 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And imagine there's going to be a lot more terms that don't have i's in them. And the ones that do have i's in them, I'll put together and factor out the I. So imagine this ix without the I, so that's just x. The ix cubed over 3 factorial without the I with a negative. X cubed over 3 factorial. X to the 5th over 5 factorial. And then let's just put dot, 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 or you can imagine what will happen next. In any case, we have the real part that don't have i's in them is just the power series for the cosine function. And then the one that has an I in it happens to be a power series for the sine function. Okay? So I do this in my Calc 2 class, but it kind of might look cool, but doesn't mean much. But since we have talked about Euler's formula already, this is another way to show Euler's formula using power series. It's kind of neat. Okay? What do you think? This is really exciting. This is what math is about. All right. So that was a little detour. Let's establish one more power series that I think will be important for us. And that is the, what did I say it was? Geometric series. Sometimes people start off with a series and then eventually try to prove that your series is equal to this function. And sometimes people just start off with this function and try to prove that the series. Well, I'm not going to prove anything. I'm just going to write down what the series is equal to. It's kind of neat because it's like the exponential series, except there's no factorials. So this is, I think it's sometimes called the ratio. No, not the golden ratio. There's neat ways to prove this. Did I say ratio? I meant geometric. This is a geometric series. Now, the first three functions that we looked at had a radius of convergence of infinity. It means it converges for every real number you think of. This, unfortunately, doesn't work like that. So this has a finite radius of convergence. Let's try to figure out what the radius of convergence is. And do you remember how to find out what the radius of convergence is? Ratio test. So let's take the ratio test. So the ratio test tells us that we want to take the limit as k approaches infinity of the k plus first term and the kth term. Now, this is the only thing that I see in this generic term is x to the k. So the k plus first term must be x to the k plus 1 divided by x to the k. Well, this is just x. Absolute value. Keep forgetting the absolute value. Now, since there's no k's in the expression, this must be constant with respect to the limit. So I can just take the limit as k approaches infinity. Nothing's going to happen because there's no k, and all I have left is x. What does this mean? Now, this is one of the things I didn't talk about when I mentioned the ratio test, was that when you take the limit of the ratio, whatever you get here is going to converge for these values that are less than 1. Maybe I should have looked up the ratio test, and maybe I should have put the results for the ratio test. Here's a quick summary of the ratio test. You take the limit as k approaches infinity of a sub k plus 1 over a sub k. And let's say that's equal to L. Then a series converges for L less than 1. Series diverges for L bigger than 1. So the main ratio test has these three conclusions. If your L is less than 1, then it's going to converge. If it's bigger than 1, it's going to diverge. And if it's equal to 1, technically you don't know what's going on. So when you're trying to find the interval of convergence, if you remember back in Calc 2, you took the ratio test and then you set this thing be less than 1. And then to find, and what you're going to do is basically your radius of convergence is going to be the reciprocal of what you get here. So, does that make sense? The number that you get here, once you get the absolute value of x by itself, the number that you get here will be the reciprocal of your radius of convergence. Do you remember taking like 1 over r business in Calc 2? Well, maybe you can look it up. So the point is that we want this thing to be less than 1, and then whatever values we get here, that's where it's going to converge. So around 0, we're guaranteed that this is going to converge between -1 and 1. Now, technically, we should try to figure out what happens at the endpoints. But I think, let me tell you now that for this one, it's going to diverge at the endpoint, so let's not worry about that. So in this case, the radius of convergence is 1, and the interval is open parentheses -1 to 1. Okay? All right, so we can do the same thing with this business by taking the integral or taking the derivative of this to get more power series. So let's do that. Let's take the derivative of this thing, of the Let's take a look at the series again, and let's take the derivative of this. What's the derivative of 1 divided by 1 minus x squared? Can you guys do that real quick? I mean, we could take the integral too, but what? Is that right? Is there a negative? So negative cancels out. This isn't worth wolframing. All right, let's take the derivative of the right-hand side. What do we get? Derivative of 1? 0. Derivative of x? 1. And then 2x. X squared. So if we imagine taking this pattern, we can actually take the derivative of the series itself, representation itself. So the derivative here is what? K x to the what? K minus 1. What? The series itself? Yeah. Now, well, I think this is it's important to have this part over here because now I'm looking at the series, and if you look at it carefully, there's something that doesn't look right here. This is not quite correct. And what is the issue? If you plug in 0 and the first term is 0, right? So, I mean, that's 0, that's fine to have 0 there. But I think in terms of the notation, maybe we actually start at 1 instead of starting at 0. So K actually starts at 1. So there's some of these little things that we're going to have to keep an eye on when we take derivatives. It looks like there's going to be a shift in our starting point because our first point, especially if our first point is a constant, then that goes away, right? When we start taking derivatives, there's going to be a little shift here. So shifting the index will be a big part of what you need to do, and you need to be really meticulous about how you keep track of that. Because the first term over here, when k is equal to 0, well, again, it's because the first term disappeared. Yeah. Okay? All right, so the radius of convergence isn't going to change here. Radius of convergence is still 1, and I think the interval of convergence is still going to be the same. But you really have to watch out for the interval of convergence. And I think what I would suggest is for you to look over the book or look over videos on YouTube on how to find the radius and interval convergence of things. All right, so we've done derivatives and integrals. We can certainly add and subtract things, right? If we add not piecewise, but termwise addition, when we add two series, we can just think about adding as long as we have the same power for some of them. So I wonder if it's time to go to a generic power series. Or maybe we'll do one more really quick one. What if we integrate this? Yeah. I think you can, but sometimes those are little things that you need to keep track of, because over here k does happen to be 0, but if you had a generic constant over there, then you want to make sure it gets wiped out. Right, the thing to do really is to take the derivative again, but I don't feel like it. Let's take the derivative again, sorry. Because we are trying to mimic differential equations, and we're going to go second, maybe third order differential equations, which means you have to take several derivatives. So let's take the derivative again. So the derivative of this is what? It would cancel with a chain rule, right? And derivative of 1? 0. Derivative of 2? What? What's the derivative of 2x? 2. What? All right, let's try again. So this would be 2, right? And then, what is this? 6? And then, really, we could have just taken the derivative of this thing. So what's the derivative of this? And with the same reasoning, wanting to make sure that we just have, got rid of that first k. K should start with what? If it starts with 0, we might be, and can we start with 1? When we start with 1 again, it's still going to be 0, so k should start with 2, right? So in your second derivative, you shift your index again by this much. Okay? So be careful. You're allowed to take derivatives of these things, but be careful when you're trying to express them with a summation sign. The indices may shift. And so when they do, you just have to keep track of the shift. All right, so power series in general. What we're going to do is we're going to represent our potential solution to a differential equation as a power series. And the way we're going to represent this as a power series is we're going to assume that our power series looks like some c sub k some constant. I don't know if they use A or C. I'll use C. And then x minus a to the kth power. So if this was an actual function that we know, then c sub k. So if this is a Taylor series, I'll say if, and I'll underline if, Taylor series, then c sub k is actually equal to the kth derivative of f evaluated at some value a divided by k factorial. Okay? If we knew the function f, but since we're trying to solve for f, we're trying to solve for a function, we're trying to solve for y, we're going to assume that we don't know what this is. We're not even going to assume that we know what the original function is, because we don't. We're just going to represent that f, the kth derivative of f value at a divided by k factorial as just some random constant c. And then there's many of these random constants, so we'll call it c sub 0, c sub 1, c sub 2, etc. So we're going to start off with this as our potential solution. And we're really just going to pick that up and plug it into the differential equation. And when we plug into the differential equation, we're going to need derivatives. So we're going to need to take the derivative of this. When we take the derivative of this, keep in mind that little shifting index. And then we're going to try to combine it to see if we can solve for these c sub k business. And hopefully, when we solve for it, we might be able to see something that is familiar to us, like if it involves a sine or a cosine or one of these, or exponential or a geometric series. And if not, then we just have to express it in terms of this power series that we're not going to know. Okay? So that's our game plan for next time, is to start solving differential equations using power series. Okay, good luck with your radius of convergence crap in your homework.